Hello everyone, I'm very honored to give a talk in this conference. This talk is based on a previous talk which was given at the Alumni Weekend in Cambridge, and that was called From a Crazy Idea to a Clean Tech Company. I thought the title is quite good for what we are talking today. So let's have a look at the outline. Okay, so I'll talk a little bit about CampSemi. I don't know if many people are familiar with this company. The context of forming CampSemi, history and roadmap. Then I'll talk a little bit about the market background, and I'll insist more on the technology, leaving the others, the marketing ups and downs, and the story continues out. So I'm going to concentrate on the first four there. That's also in the interest of time. Now, the background research. I've been with Cambridge University since 1991. I did my PhD in King's College. Then, at the time, I was actually one of my friends here who is the organizer. We were playing football together in King's College. So it happened that we knew since then. In 1998, I was appointed a lecturer. And basically, during my time as a lecturer and then as a reader and now professor, I worked with many of these companies, Fuji Electric, Toshiba, Dynex, Infineon, Philips, and some of them for 10 years or so. Our experience was that there were many innovations, but no products. Interestingly, companies have filed the intellectual properties, the patents. However, we found that the ideas emanating from outside the company, in particular in our university, was always prone to a political disadvantage. That's so-called the not invented here syndrome. And often we found that during the duration of the project, by the time we've seen the project to a particular stage where we could have gone in production, the internal champions of the project were moved to another position. So promoted to other activities, another person would come, take care of our project, he wanted to change something, to make his mark, and often these projects led to nothing. So that is the market background. We decided in 2000 to form a company to exploit our inventions. And basically the background of the energy market there, as you know, the electricity is fastest growing source of energy. We have over 10 trillion kilowatts hour of electrical energy generated per year, and over half of this energy is currently wasted. Just as an example, linear adapters charges are less than 50% efficient, and if you look at the incandescent lamps, they are much better heaters than lights. So we believe that more efficient power conversion is key to energy saving, more people using the existing supply infrastructure, and smart power conversion can save a lot of the natural resources, so there is a noble aim behind it. It's not just coal, oil and gas, but we can also save steel, copper, plastic and so on. And lower costs with lower waste and recycling impact. Now, interestingly, I don't know if this picture is familiar to you, but actually this has progressed a little bit since I've seen it the first time 10 years ago, but it's remarkably poor in terms of where we are with the efficiency today. In the lighting sector, we talk about 20%, less than 20% overall. This is the world picture. Motor control, slightly better. Power supply has increased a lot, but it's still below where we want to be. So we are at 60%. Generally, we want to be well over 70%, and in some applications over 80 or even over 90%. Then automotive is also 30%, electrical conversion less than 50%. Overall, we are basically less than 50% efficient, so we waste a lot of energy. Now, the application space in particular for us as a company, we basically do look at the AC to DC market. In effect, everything that is connected to the AC mains with 110 to 230 volt supply, then with our chip, we regulate the power. And the point is that during this regulation process, we try to deliver extremely high efficiencies. Now, where we are in terms of the power, if you are looking at the power and the market size, there are some applications which have extremely high market size, like the mobiles. But there is also a nice soft spot in the middle where basically you have something like modems, you have other types of phones, you have peripherals, you have the white goods like the washing machine and so on. Interestingly, since I put this picture, actually we did move into the mobile market. So as we are talking today, we are basically having contracts with large companies in the mobile market. A bit about the history of the company. So it was founded by Professor Amaratunga and myself in August 2000. And the idea, as I said, was to commercialize power integrated circuits technology developed in our group at Cambridge University. We had decided to cut some of the projects with some of these companies and decided to go via this route, commercializing ourselves. I also acknowledge Tanya Trajkovic and John Lee, who were part of the founding team. They are not founders, but they were part of the founding team and instrumental in shaping up the company. We've been through an interesting route. We started with a Smart Award. We've been given even the Rising Star of the Year. Since then, we had a string of awards, which I didn't put down here. Interestingly, we delivered the proof of concept in 2002. When we started the companies in 2000, we had only an idea, and it was only proved by numerical simulations by the computer, but it turned out to be absolutely correct in 2002. Then since then, we raised 30 million pounds capital from venture capital from a consortium led at the time by 3i. Scottish Equity Partners, TTP Ventures were part of it, and more recently we have Harbour Trust and Bank Invest present. The company in progress was an interesting progress. We started with university funding. It took quite a bit of time to prove the concept. In 2004, we had basically the CEO joined. That was an important thing. We had some alpha partners sign up to this program. We started our Taiwanese office. Between 2002 and 2007, we had a B round, what we called, followed in 2007 by the C round, which was by far the largest, around $26 million invested. Effectively, we started with the revenue. I must say it took us 7 years to get to the revenue. We had extremely good IP, and I must say that the investors were pretty sort of lenient to us to allow us to be 7 years without revenue. However, they did see the potential of the technology and the potential of the company. So in 2007, finally, we had revenue. 2008, we shipped 10 million units, and then we had a very, very rapid progress. Effectively, every year, we double our revenue. And now we are in 2011, we shipped over 120 million chips worldwide, and the prospect looks very bright. Now, what was this based CampSemi on? So what I'm going to show you here, it's the technology that led to the spin-off of CampSemi. Right, this picture was supposed to rotate. This is a power supply, just a big picture of power supply. If you just open one, all you see there, you see a big transformer, lots of capacitors and so on. On the other side, however, what you don't see here, if the picture rotates, which couldn't be done in PDF, you see a tiny chip, which is the power IC, which controls the whole energy conversion from the AC mains to a DC regulated power. In that power IC is in fact what we have, what I show you here. There is a controller and a high voltage power device, which is in series with the primary of the transformer. So that basically regulates the power. That basically has to deliver the voltage at the output constant indifferent of the load. The power device, we called ourselves not a mixed signal, because we are not only analog and digital, but very mixed signal, because we also have power in it. So in a single chip, we have basically mixed signal controller, which is analog and digital, and in the same chip, in the large area there, you can see the high voltage power device. And roughly, depending on the application, depending on the power, it's half-half. For lower power, the power device is smaller. For higher power, the power device is higher. Now, what is, however, our technology, in what we differentiate from the rest of the world, is that we started with something called power brain, power on a thin silicon membrane. Unlike everyone else in the field, our wafers are transparent. You can see through. The hand is actually behind the wafer. I will show you in a second what it is. And it was based on this simulation, and intentionally put a simulation which was done in 1999 by myself before forming the company. And basically, you see what happened there. This is a lateral DMOSFET. I don't want to get into too many details, but it's basically a high voltage power device. And if you look at the picture on the left, you see some crowding of these potential lines, so high electric fields, both at the drain side and the source side. Now, the whole idea is what happened if we remove the substrate, which is the silicon substrate, under this region, the drift region between the gate and the drain. Interestingly, all this potential drops down into the substrate underneath, into the air gap underneath, and becomes extremely uniform. When we'd seen this, we actually advertised 20 times increase in the breakdown voltage. And actually, we did deliver. It was a 20 times increase. And interestingly, there was another aspect of it, especially if you employ a bipolar device that comes with a lot of charge. If you keep the substrate, a lot of this charge is distributed deep into the substrate. That's a well-known effect, but it's a very detrimental effect. One, because actually it takes a long time to remove the charge from the substrate, from the silicon wafer. And second, is that this charge can travel somewhere else. And where, in particular, it can travel actually to the CMOS circuits, to the controller, and affecting the operation of the controller. So one, the problem with speed, and second, interference and isolation. So what we decided at the time, how about if we cut the substrate under the drift region? And not cut it just by half, but cut it very significantly to leave an extremely thin region. And our region is so thin that it becomes transparent. So, initially we started with a very, very thin membrane. We started with only 0.25 micrometer of silicon. Then we increased it to about 2 micrometer, and we found that about the sweet spot is about 5 micrometer. So the membrane itself is only 5 micrometer, and we have all the charge now compressed into a very thin region, and because it's all at the surface, basically we can deplete it very, very fast. The device becomes very, very fast, and because it's all confined into this thin membrane, it cannot travel anywhere else. So it doesn't affect the other circuits around. Now, particularly what is important is that we can actually have a bipolar device on this thin, very thin silicon membrane that can run at extremely high frequencies. And one interesting thing here is to compare this CAMSEMI bipolar device, it's called lateral insulated gate bipolar transistor, LRGBT, with a device which was known to be very fast, which is a vertical MOSFET, which is not a bipolar. Interestingly, we found that our device was much quicker, and in fact, we had a demonstration that the switching speed increase is about 5 times. So you get a breakdown increase, you get a switching speed increase. Now, what, however, was very difficult and why it took us such a long time to produce such a device is actually to make these membranes basically stand reliability tests, is to package this. As you can see, you have all these air gaps. You have actually multiple fingers. Under each of these fingers, you have an air gap. And basically to withstand, for example, the pressure of the molding compound above, to make sure that the die attach, which is under the chip, does not climb onto the air in the membrane and so on. So there was a lot of development. I spent 2 years of my study in reliability, something that we don't normally tackle in the university environment, but I was forced to do 2 years of reliability just to try to make sure that this chip is actually working for a long time, not just proving the performance when we first tested. Now, speaking about the performance, it's quite amazing to see where the competition is, where the competition was. Best in its class is a standard high voltage switch, comes from Power Integration. I can disclose it to you. And it's about 10 times higher than what we can deliver with absolutely the same performance with a Power Brain. That's one way to look at it. Or the other way to look at it, we can make it in between, still save cost, and deliver higher efficiency. Interestingly, when we started the company, there was very little about efficiency. The investors were very much attracted by the reduction in the cost in the silicon chip. They were also very attracted by the fact that we can do high speed, because if we do high speed, it means we can shrink the passives around the capacitors and transformers, so we can shrink the power supply. And they were absolutely uninterested at the time in efficiency, because there was not much about efficiency in those years in 2000. However, the things have changed. Now more and more is put onto efficiency. And actually how we advertise this, we advertise as a very, very efficient chip. So we are not trying to go to very low, but we are trying to get in between. Now, just to close on this Power Brain technology, it's originated from research conducted at Cambridge University. It's very elegant. It looks like a simple concept. It's actually very simple in terms of the concept, quite difficult in terms of manufacturing, but we've gone through these steps. And what is interesting, differentiating CAMSEMI from the rest of the world. A technology that had a noble aim to improve significantly energy efficiency for power system. And at the time of creation, a technology was ahead of its time. Interestingly, we were just about in time in terms of filing the IP, because after we file our IP and patents, there were several other people coming with very similar ideas. However, we are definitely ahead of time in terms of manufacturing and in terms of other foundries being able to this beautiful edge to get the membranes and so on. Today, however, we have a lot of people who are very much interested in this technology. Interestingly, in exactly its form which I presented here, it hasn't gone to market, but we do have something based on this in the market today. So this is the end of my